Joseph Huang.
Hi, my name is BCU.
And my name is Angel Spinoza, and our project is the full bridge inverter.
We start by adding 12 volts to the top of the MOSFETs. We start by turning on the left P channel and the right N channel, while keeping the other MOSFETs off. In doing so, we will have current going through the MOSFETs that are on through the load, thus creating a positive voltage. Then we're going to turn off all MOSFETs so that we can create a dead time, because we are going to make a quasi waveform. So we're going to turn off all MOSFETs. And we're going to create that dead time that's going to happen right now. Next, we're going to turn on the other MOSFETs. So we're going to turn on the right P channel and the left N channel. And then we're going to create a current that's going to go the opposite way. And that's going to create a negative voltage. We're going to turn off all the MOSFETs again to create the dead time so that we can have a perfect quasi waveform. And then the cycle is going to repeat again and again. We now have resistors that are pull down and pull up resistors, mostly just to keep the MOSFETs off. We also added 10 ohm resistors so we can protect MOSFETs. And just in case we have an inductive load, we were wondering what's going to happen when there's a dead time, since it's going to create an EMF. With that, we added diodes from the source to the drain of each MOSFET. So when there's a dead time, current's going to go through the load and just go back to the power supply. And also, we decided to add a capacitor just so it can store energy and send it back to the load. Next, we were looking at the transformer. We got a transformer that went from 10 volts RMS to 120 volts RMS and sent the quasi through the 10 volts so they can come out 120 quasi waveform on the other side. Keep in mind, all of this was 60 hertz. The filter that we used was an LC filter. We had 6 1 microfarad capacitors in parallel to the transformer, which the transformer was 1.1 Henry. And in doing so, we had a frequency of around 60 hertz and creating a perfect sine wave. Now that we got the basics down, we decided to solder everything together into a 3D printed casing. We also had to add a voltmeter to read the voltage on the input and the voltage on the output. So in that case, we decided to get an LCD display that can tell if there's a short circuit or when it's on. In this case, we used a short circuit protection board and connected it to the LCD display. Once everything was connected together, we turned it on, and as you can see here, it can detect if it's a short circuit. And by resetting it with the button, it tells us to wait, and it can read the voltage on both sides. Right here, we turned on a light bulb, and you can see that the voltage on the output was changing because of the load. And thus, we have a full bridge inverter.